be here today. Okay, and hopefully you notice this on Canvas, right? The first thing on each module, I always kind of tell you like what to read and stuff like that. And as we switch out of the textbooks, you might notice that we're running out of chapters in the textbook, right? Um, the topics we'll be covering will be outside the textbook, but I'll still be referencing like parts of the textbooks. So, for example, since we're talking about modulation, which is we'll tell you what that means right in a second, right? I have some notes myself, right, on modulation. There's also some notes from a MIT open course that you can take a look at. It's the same material. I think they do a little bit more advanced, but so when you run into that, just see it, and then but don't worry about having to do any math and do anything in the lab about that. But right, these notes also refer back into the textbook. 4.5 is about diodes. 4.6.6 is about functional feedback, which I skipped in chapter 6 so that we can talk about this today. But this whole module is going to be on you being able to basically build a wireless transmitter from, well, one side of your breadboard to the other side of the breadboard, but you could just make that fiber optic as long as you want, actually, and you just need a more and more powerful LED or laser in order to do that. And hopefully that'll be a fun thing. And that basically kind of wraps up our analog part of our course. Okay. So, any questions before we get started? Like how to deal with these weird reading material, sometimes inside the book, sometimes outside the book. Okay. So the notes are just right beneath it, also, right? Okay. Don't let these like numbers trick you, right? Even though this is the MIT module number, right? Not our module number. Okay. Okay. Everyone happy? All right. Now, I don't know if people still use this phrase. Do you guys know what this means? Information age? This is when I was growing up. I think people call it the information age when computer first started appearing, right? And the information age, right, is kind of this little funny drawing where you can say that the postal service is a information carrier, right? We can say that, oh, that's when information start being sent around. Um, and then people started getting typewriters. I don't even know what this is. Oh, this is Morse code. So you do a little telegraph there, right? And then people started having cars, right? And then in the 20th century, right, we start building telephones. And telephones are like cell phones, but then attached to wires. Okay. And then in the 70s and 80s, right, we started getting computers. I don't know what this is. Bicycle runner? I don't know what this is. But anyway, and then we come into like cell phone and our little tablets, right? And your laptop computer and all of this stuff that evolve over the last couple of centuries, right? But the key word is that all this is about information, right? Information is very important for today's society, and you can transmit information either through wires or without wires. So the ones with wires are called wire communication, and I think I gave some examples of wire communications already. But what do you guys think wire communication? What are devices that uses wire communications? Ethernet, yeah. So computer, yeah, it's called Ethernet. Sometimes people call it, the heart wire or something like that, right? Uh, what are other examples of wire communication? I'm sorry? Fax. Wow, cool. Fax machines. Okay. Fax machines. At least fax machine that works over the telephone line, right? Okay. And then if you go to my office, I don't think we have one here. Like this school still use telephone that has wires on it. Okay. And I think that's a good thing, like, because sometimes the wireless does go down, right? And it's just a more another I wouldn't say more robust. Just it's just another form of communication that oh, if the wireless gets cut off, you have the wire. If the wire gets cut off, you have the wireless, right? It's just a good backup. What about other types of information transferred through wires? Cables from where to where? Yeah, cable. Yeah, cable television. Okay, right. Okay, and this is going to be kind of fun, right? Because we're going to actually, what you're making is pretty similar to that in Lab 7. Um, what about something you guys are doing in here? Do you communicate one device to another in here ever? The probes are getting the scope probes are getting information from the breadboard, right, um, onto the screen, right, of the scope. Is there something else that are also wired communication on your in the lab? No one else? What else have information in it? The function generator, right? So so this is basically kind of like the output, right? And then the function generator, this is down here, right? Generator is the input. Okay, so you have the function generator, sending stuff into your breadboard, and then you have your oscilloscope reading it out. Okay, so you already do wire communication in this lab. Okay, and we're gonna see how we can do that better in an environment that's more noisy. Okay, especially wireless communication. Okay, wireless communication. So I'm not gonna, you guys can yell out examples, right? But I'm gonna start listing them, right? Like, for example, your cell phone. Okay, you guys can chime in more if you want. Like the Wi-Fi router. I'm sorry. Your laptops, right? Laptop, right, uses Wi-Fi, right, in order to communicate with each other. Satellite, right? What kind of radio? Radio is very general, actually. Okay. Like car radio or something? Car, car. Walkie-talkies, okay. Walkies. Um, Bluetooth, yeah, that's another, right? It's very similar to Wi-Fi, actually. It works on the same frequency, yeah, but it's much shorter range. Any other wireless that you guys can think of? Right, right. Technically, it's kind of wire, kind of not wire, right? Fiber optics, okay? The reason why it's considered wireless is because you're sending electromagnetic waves guided by a tube, right? You're not transferring, electrons over, but it is kind of a wireless. It is a wireless communication where you're not sending electrons back and forth, right? Okay. Um, so this is just a little diagram, right? Did we miss anything? So you have like some ground station that can either receive satellite, right? And then you have a car, right, that will have maybe a satellite receiver on it. And then in your house, you may get cell signal, right? And then and these cell signals can communicate with your PCs, your iPhones. Does that really say iPhone? Oh, IP phone, Internet Protocol phone. And then cell phones and stuff like that, okay? Right? So all of this is useful, and all of this is based on something that we're going to talk about in these two lectures called modulation and demodulation. Okay? Okay? That might not sound very familiar to you, but if you shorten this to one word, it's called a modem. Okay? And that's exactly what your modem does. Anyone ever had to deal with modems in their house? Anyone not seen a modem before? Everyone seen a modem before? I can bring in mine, and I'll just disconnect my internet for a while. Okay? Okay? And that's what this week, this module is going to be about. Okay, so why do we need to deal with the modem, right? Because you guys are able to send signal back and forth from your breadboard into your oscilloscope and into your function generator and all that stuff, right? So why do we need this new thing, right? And the reason for that is this thing called noise. Okay, you already seen this actually when you're on your when you connect your function generator just directly to your breadboard, right? Sometimes you get a little fuzzy on the scope, right? Right? The signal is not as clean, right? And the idea of noise is that if we had, you know, let's say I'm trying to send you a sine wave, right? You know, it's perfectly crisp like this, right? This is like V in as a function of time, right? If you connect this through some wire, right? Some wire or wirelessly, right? Either through, you know, let's say this is your function generator, right? And this is your scope, right? You may start to see like a little bit of wiggles on top of it, right? It's not as, you can still see the shape, right? It's still the same shape, obviously, but there's a little bit of a fuzz in it. And this fuzz is the noise in the line, okay? Okay. And you guys already know how to deal with these noise a little bit. The first thing one thing you can do is filter them out, okay? So for example, in this case, is compared to the noise, the picture on the left, would that be a low frequency signal or a high frequency signal compared to the noise? It's low, right? Because the wavelength is very long, right? Long wavelength means low frequency, right? Where the noise is very high frequency. So from what you guys already know how to build in the class, what kind of filter would you put on this in order to remove this noise? Low pass filter, right? Okay, and that's going to be, oops, right? That's just putting a capacitor and a resistor together, right? Okay, right? And that will allow you to remove this kind of this fuzzy noise, right? And the frequency that you want to remove it at, you know, is going to be determined by, you know, the F3 dB point, right? Of whatever your filter decided to be, right? Okay. So all this stuff that I've been teaching you guys, right, is useful, hopefully, right? Not only can you filter it out, let's say, right, if you know, okay, I know that the frequency of the signal is 120 hertz. I know the frequency of the noise is, you know, maybe, you know, 1 kilohertz to 100 kilohertz, right? That means I can actually filter in that signal, okay? So what type of filter should I use in order to filter in a particular frequency that I'm interested in? Anyone else? Real? High pass? High pass will allow you, so for this example here, right? A high pass, right, will give you this fuzzy stuff, right? But you want to keep the 120, right? How would I keep only the 120? What type of filter? I remember. You guys built both of them. Yeah, the band pass filter, right? Okay. Okay. So a band pass filter allows you to pick, you know, a resonant frequency, right, with some bandwidth around it, right? So there's going to be some bandwidth that you can determine by changing L's and C's and R's, right? I don't remember what the equation is, right? And you can pick that so that, let's say, right, even though you say this is 120 hertz, right, this could be, oh, it has a uncertainty of maybe 20 hertz, right? So it could be a 10, you know, 100 hertz, 140. So you want to make your bandwidth wide enough so that it can still pick up, right, 100 hertz and 140 hertz, right? Make sense? Right? Because the bandpass filter, right, the dot plot actually is like this, right? This is 0. Over here is this attenuation in decibel. Right here is like frequency over the resonant frequency. If you set it at 1, right? It's a very bad picture, right? Remember the bandwidth is this width down to the F3 dB point, right? Right, there's two of them, right? So you want to set this, basically this F here, oh sorry, F res, not the F, because you have no control over F. You want to set F res at 120, but you want to make this bandwidth, you know, plus or minus 20 hertz, plus 20 hertz. That way you can still pick up signal that are a little bit off the resonance, okay? So that's kind of like what you guys know already, how to deal with noise, okay? There are other ways to deal with noise, which is like you can shield or screen from the noise, okay? If you ever go, if you're ever talking on a cell phone and you're walking around and then you go in the elevator, what happens to your conversation usually? Yeah, you lose the signal, right? So that's essentially what happens when you get shielded. It's because most elevators is basically a big metal cage. The metal cage is to keep you safe, right? Right? And when electromagnetic waves contact with a very good conductor, the good conductor actually absorbs that wave very well. Okay? Basically, the elevator box is a antenna, but the antenna is absorbing all of that electromagnetic wave and not allowing to pass through. Yeah.
So I don't know if I've seen this happen before, with modems specifically, where if I think it's if they want to amplify the signal or concentrate the signal, they'll get an aluminum can and put it around the antenna.
Right. So that's a way of actually reflecting the signal. Okay. Right. Speaking of signal, right? So okay, so let's finish talking about the elevator situation, right? So you know the elevator doors open, right? When the door is open, some of the signal can still sneak in through the door, right? But once you walk in, right, and then the door closes, you're basically enclosed in a metal shell, okay? And those waves can actually not pass through, okay? Especially you know, depending on the thickness of the elevator walls, okay? But to Ivan's point, what happened is that when the conductor absorbs the electromagnetic wave, what's really happening is that the electrons in the metal is like wiggling up and down. Okay, when it wiggles up and down, it can also release that energy back out. And when it releases that energy, it's actually just kind of going outward, you know, isotropically, meaning there's no predetermined direction, but it cannot emit that out into the elevator because, right, what's the layer that's actually absorbing the signal is just on the outside, and inside the elevator, the electrons aren't moving around. Okay? So, to Ivan's point, is that I think, so I have made this myself to get a better Wi-Fi signal. You take a little Pringle can, you cut it in half. People don't do this anymore. You cut it in half, and basically you stick your Wi-Fi antenna right in the middle of it. Okay, okay. And what's happening is that, well, I know that, right, the other device I'm trying to communicate to is in front of it. You don't want to communicate with the ones behind it because this is actually going to shield it. Okay, but if you put a device in front of it, right, any signal that comes in, right, not only catches the antenna, but then gets reflected off this wall and comes back to your antenna twice. Okay, so you just have it's basically like kind of like a satellite dish. Okay, so those of you ever had people even use satellite dish for TVs anymore? I don't think that's a thing anymore, right? Yeah, yeah, yeah. Maybe in like remote areas, right? Okay. So that's another way you can. So this is like, you know, it's not shielding, it's um, concentrating the signal. I don't know what it's called. Amplifying this. I don't think you want to use the word amplify because amplify, we have a special word for that, right? Focusing the signal, yeah, so that you can actually catch it with a small antenna. Okay. All right. So that's another way to shield. But the problem is that shielding a lot of times basically removes all of the signal, right? It doesn't pick out a particular frequency, right? So that's why usually what happens is that when you have an experiment that's very sensitive to electromagnetic wave, you put it in the metal box, right? And then you just have the two devices inside talking to each other, right? And it's blocked from the outside, okay? Um, So let's talk about, like, what frequency of these noise are, right? And this is here is a kind of a complicated plot. I don't know where I got this from, but I think I looked it up. It's somewhere in the UK, right? Where if you were to go outside and then just stick an antenna up in the air, you will be able to detect, okay, noise that are in the range of 1 megahertz. So this is this frequency in megahertz. So 1 megahertz, right? You'll be able to detect about 60, okay, times negative 174 decibel, okay. It's some weird units, but right, this is going to be some noise that you can detect, okay. And as you go lower in frequency, this noise just increases kind of exponentially, okay. All right. So the noise in the air when you just step outside tends to be low frequency noise, okay. Low frequency electromagnetic waves that are always interrupting your signal. As you increase the frequency, this noise drops down. There's actually a little hump here, okay. All right. And this is actually due to like a atmospheric noise that's actually created by cosmic ray hitting the upper atmospheres and causing our nitrogen to oscillate up and down. But we don't have to go into that. There's a little hump here but the idea is that, well, once you're above 20 megahertz, right, the noise almost basically goes away, okay? All right? Okay. So that's why a lot of wireless communications happens at, above 20 megahertz. For example, your car radio, I think it starts off at 80 megahertz, right? And then your cell phone, right? I think they are usually around 800 megahertz. Okay, if you go into your cell phone, look at your little cell phone setting and figure out which band it's using. So when they say band, it's actually the frequency. You're gonna see that, I think usually it's 800 megahertz or 1.6 gigahertz or 1600 megahertz. Okay. So usually you're doing wireless communication out here to stay away from the noise just due to nature being around, okay? Right? Okay. Besides natural noise from just our, you know, nitrogens moving around in the atmosphere, okay? There's also this thing called Johnson noise, and those of you taking experimental with me next semester will get to play around with this. I think the setup is actually next door, not over here. Okay. Johnson noise is also known as thermal noise. So if you imagine a little resistor, I'm not going to draw the symbol, just draw a little piece of ceramic, right? Usually you would connect, one with a high voltage to drive current through it, right? This is just a piece of ceramic, okay? These little pieces of ceramic are made of what? What's everything made of? Atoms. Yeah, thanks. I know it's kind of a weird thing to think about, right? And these little atoms have electron clouds all circling around it, okay? Right? At non-zero temperature, these atoms are vibrating, okay? Everything is vibrating as long as there's not absolute zero, okay? This vibration kind of jiggles around, and then once in a while, what happens is that it'll get close enough so that the electron can actually escape the resistor, okay? So once in a while, you get a little electron leaking out of here, and once in a while, you get an electron leaking out of here from both sides of the resistor, right? So if you just connect a resistor, right, and try to measure the current across it, on average, you get zero. Does that make sense? Because sometimes you get one going to the left, sometimes you get one going to the right, right? So on average, if you average over maybe on the order of a millisecond, it averages to zero. Okay, but if you look at it maybe like an instant, like a picosecond, right, you may have a current going to the left and then you get a current going to the right. You just have this oscillation. Okay. This is known as thermal noise or Johnson noise because the person who quantified it is named something Johnson. I don't remember what his first name is, but this is basically a thermal effect. And whenever you think about anytime someone says something thermal, it's always going to be related to this guy, Boltzmann's constant. Okay? All right, there's always going to be related to this crazy guy, well, this German, not crazy guy, this guy, and I think he's like German, or Austrian, forgot where he was from. But, right, because you can actually measure the voltage difference across a resistor without any voltage source on it. The resistor itself generates a voltage just from the thermal noise of this electrons, moving out to the right, moving out to the left, just a little bit. On average, that voltage turns out to be 0, okay? But, right, just like when we talked about, right, AC voltages, right? This is, voltage as a function of time, right? Right, the average of an AC voltage is 0, right? V bar is 0, right? But we can still quantify this number called the VRMS, right? The root mean square of that voltage, right? So for example, even though the average voltage coming out of our wall is 0, right? The RMS voltage coming out of our wall is actually 120 volts, right? Okay. Same thing here, even though the average voltage that's coming out of this little resistor just by connecting your multimeter to it and nothing else, okay? The average is 0, but you can actually calculate the RMS value of it, and the RMS value of it can be I'm not going to derive it because this requires like a thermodynamics thing, right? It's just the square root of 4 Boltzmann's constant, which is this number here in SI units, times the temperature of your resistor, which is neat, right? The hotter the resistor, the more noise you get. So if you cool this down to absolute 0, you actually get no noise, okay? Right? Because that's when these atoms stops moving, right? Okay. So this T is going to be in Kelvin, okay? So it has to be in Kelvin, okay? R is the resistor's value. It's just, whatever you have, the 1K ohm, 2K ohm, whatever it is. Delta F, that's a little bit more complicated. This is the bandwidth, once again. Is how wide of a frequency you're trying to measure, okay? And those of you who will be with experimental next semester will actually get to measure this yourself. So the Johnson noise on a typical scale on a little resistor that we're using, okay, is going to be 0.16 microvolts, 160 nanovolts. Okay, so if you connect that to your multimeter, you're not going to see it, right? Okay, or if you connect it to your oscilloscope, you're not going to see it. Okay. In that lab next door, you actually will be amplifying that signal by a factor of like 1,000,000, and then you can actually see this voltage, okay, which is sort of neat, okay? The bigger the resistor, the bigger this Johnson noise is. So if you have a 1 meg ohm resistor, you actually get about 4 microvolt. Still super small, so nothing compared to what you guys are measuring in the lab, right? So in the lab, the smallest thing you're probably looking at is maybe 100 millivolts, right? So this is going to be, I don't know, 2,000, 2,500 times, 250 times smaller than that, right? Okay. All right. So, so this is just a little plot that I found on the internet. You don't have to, take notes on this. But for a, let's say you have some resistor that's 1 kilo ohm, right? The bigger the bandwidth you're measuring, the bigger this Johnson noise is. That's because you're including more and more frequencies of these electrons that's going in and going out of your resistors. So the more frequencies you're including, the more you're capturing. Okay. So ideally, right, this delta F or this bandwidth thing, right, should go to infinity. But in reality, we can't measure from 0 to infinity, unfortunately, right? So we measure in this little box called bandwidth that, we're going to measure from 0 to 1 megahertz, okay, and see how much noise comes out, okay? Okay. Any questions about this? So especially those of you taking experimental next semester, you'll get to actually do this in real life. I guess we could have made a lab out of this in this lab too. All right, the other one is a little bit more towards related to quantum mechanics, where it's called shot noise, okay? And to me, this is the easiest way to understand it. Other people explain it different ways. Um, Way back before there were transistors, there's these things called vacuum tube. And the working principle of a vacuum tube is that you have a little wire that can be heated up, okay? And a lot of times when you heat up a wire, it gives off electrons. It just kind of floats away because now the electron has enough energy to escape the metal, right? Remember that conductor, right? Electrons can move around very easily around on the conductor. So if you just heat up the metal a little bit, the electrons actually escape from it, okay? What you can do is that, well, if you put a negative, if you put some positive charge on this side and some negative charge on this side, right, the electron will start floating from one side to the other, right, because the electrons are attracted to the positive charge, okay? Okay. You can set this up by just putting a little battery, right, across it, okay? So this is the, how a vacuum tube works, and this is how we actually used to amplify current, just like a transistor, before the transistor came about, okay? And each of these will be like this big, okay? Okay. And the shot noise is created, right, when, right, even though there is actually not enough voltage to bring an electron from here to here, right, just from the fact that you have, a few electrons floating off, right, and those get accelerated towards the positive charge. These are called shot noise, meaning you get one electron shooting out at a time. Okay, the charge of one electron is very small, right? The thing is, right, you will have a little bit of this, and this is also a very small number. So as opposed to just a voltage you get from Johnson noise, the shot noise is a real current that you can actually measure. Okay, the way you calculate the shot noise is, once again, there's a square root. So you see all these equations has to deal with square roots. Okay, 2 times the charge on one electron, okay, times I naught. I naught is going to be dependent on which device you're dealing with, okay? Okay, so for a 1 kilo ohm resistor, it'll have a I naught of something, okay, maybe on the order of microamps, okay? But 1 meg ohm resistor will have an I naught of a milliamp, okay? It's just the fact that more material you have, the more chance for it to flick out an electron, right? And then you capture it on your side because it's inside your circuit, and therefore now it looks like it's a real current that you made on purpose, but it's just electrons being flicked off of a surface of a material. Okay. So if you once again, we have this bandwidth delta F in here. So as just an example, if we have a I naught of 1 milliamp, so for example a 1 meg ohm resistor, right? And some bandwidth of a kilohertz. The charge of an electron is of course 1.6 times 10 to the negative 19, right? You will have a shot noise on the order of a nanoamp. Okay, not that big. Okay, but not that big unless you're trying to measure things on the order of picoamps, right? Then it's crazy, right? So what you guys are doing, you guys are measuring something on the orders of milliamps, right? So you guys are not too worried about this, but this is going to be a problem when you have a signal. Let's say you have an antenna, right, and you're capturing the wireless signals out of the air, right? The amount of current that antenna actually generates is on the order of a nanoamp. Okay. Okay. So, um, so unfortunately, right, what I just showed up here. So these are kind of random noise. Okay. Right. And then up here, I show you guys that, well, the noise in the atmosphere tends to be low frequency, right? And the thing is, right, the information we're trying to send to each other, for example, me talking to you, is also low frequency, right? So remember that, the human, our hearing range, right, goes from about 20 hertz to about 20 kilohertz. If I have your ears, right? Mine is actually only goes up to 14 kilohertz because I'm old, okay? So as you get older, you lose your high frequency hearing. So this is very low frequency, Okay, right? Another example is that when you're watching TV, if you have a really nice TV, it has a refresh rate of 120 hertz, right? Or if you have a cheap TV like I do, only refreshes at 60 hertz. Okay, um, and that's low frequency, right? It's only 60 times per second. Okay, so we need to send all of this information over this low frequency noise, this low frequency information over a low frequency noise, right? And now we're screwed, right? Until, guess what? And I'm sorry? Yeah, until we use a modem, okay? The idea of a modem is that you take your low frequency signal, your TV or your voice or whatever it is, right? You have this process called modulation, okay? And this process of modulation basically has so this is low frequency, right? Mixes, technically actually multiplies, it multiplies it by a high frequency carrier signal, okay? And then you send that out into the air. Now it becomes a high frequency signal that's, that's above the noise, okay? And then what you need to do is capture that and then demodulate it, okay? Once you modulate it, after you capture it, you have to demodulate it to basically get the information out. It's kind of like a little bit like encoding, like encrypting information, but it's a dumb encryption because everyone knows how to do it, including you in about, in 3 days. Okay. Okay. So, so, so we use modem. So this is a modem. So this is a ADSL line, asymmetric digital subscriber line, right? And this is just a signal that's being sent over your telephone line, okay, right? And then that turns it, and so this is the DSL modem, right? DSL modem, okay, right? And then cell phone towers, of course, has to have a modem inside, right, in order to send the signal out and then receive the signal. So when you send the signal, you modulate the signal. When you receive the signal, you have to demodulate it in order to get the information back up. Okay? So there's actually a modem inside your cell phone also. I don't know how to draw a cell phone.
So R2
Yeah.
and modulates it from like a low frequency to a high frequency.
Right. It takes the low frequency information, multiply it with a high frequency carrier frequency, and then you mix them, you multiply those things together, and then you'll see that it comes out as high frequency. And we're going to do the math on it in a second, okay? All right. So that's a good question, right? And you don't have to believe me, and you just have to believe, technically you just have to believe algebra. It's pretty simple, actually. Make sure I'm doing the right steps. So let's say, right, I have some signal frequency, f, as a function of time, f sub s, right? And it has some amplitudes, I don't know what it is, doesn't matter, right? And, let's just model this as, not just model, let's just take the assumption that this has some form that's cosine, right? It could be sine, but we can just shift it by 90 degrees and it'll be a cosine, right? Okay? And it has some low frequency, right? This is where this f is kind of confusing, right? Okay, omega is the frequency, f is the function that we're trying to send, right? Okay, so make sure that's clear. Sorry about that. I think I took this from an old notes, okay? Okay, right? So this is the thing we're actually trying to send, right? So this is the signal. I'll draw a little box here. What I'm going to do is I'm going to mix it, or technically multiply it, with a carrier signal, okay? I'm going to combine these together with a modulation. This is the mod part of modem, okay? And then what's going to come out is going to be the modulated signal, okay? Okay, so this is f sub s. This is going to be f sub c, right? F sub s is the signal, f sub c is the carrier. You mix these things together, and then you're going to get a modulated signal coming out, okay? So let's define what the f of c is. Also mean it's the same thing, but all we know is that omega c has to be much bigger than omega s, right? It just has to be higher frequency, right? So let's say omega s is 120 hertz, right? We're going to make omega c, right? Let's say 120 kilohertz, 1,000 times faster, right? Technically, this is not hertz, right? This is 1 over s. Okay, kilo 1 over s. Okay. Okay. Actually, the way I wrote it, okay, it's fine. We'll just leave it like that. Okay. All right. So the way we do modulation is that we're gonna just multiply these two numbers together, these two functions together. Okay. Right. So the modulated signal is just f sub s times f sub c. Okay. They both depend on time, so it's gonna get some funky, you know, cosine waves that are multiplied together. Okay. So if we did that, right, the constant part just kind of pulls out in front, right? Right, they're just constant. Okay, what you have then is a product of two cosine functions. And this is where your trigonometry teacher tells you that at some point in your life, trigonometry is going to save your life, right? Why? Okay, when you have two cosine functions multiplied together, that's a trig identity, right? That allows you to split them. Okay, so I'm not going to copy down the trig identity, but I'm going to describe how it gets split. So there's always going to be a 1/2 in front, okay? It's going to get split like this, whereas cosine is going to get a little bit more boxes. Omega c minus omega s plus cosine of omega c plus omega s. Okay. Okay. So if you don't believe me, just look up the trig identities for cosine A times cosine B, right? And it's going to tell you that it's going to be cosine A minus B plus cosine A plus B, right, with a 1/2 in front. Okay. Yeah, David? Oh, yeah, the time is still there. Yeah, sorry. Okay, so that's why I have two parentheses. Okay. Omega c minus omega s, all multiplied by time, because they both have this time common, right? Okay. Omega c plus omega s times time. Okay. All right. Since omega c is much smaller than omega c is much bigger than omega s, right? Well, if omega c is 120k, right? Omega s is 120. What's omega c minus omega s approximately equals to? Right? Basically, it's going to be omega c, right? Approximately. What about the plus? It's also approximately omega c, right? So by multiplying your low frequency signal with a high frequency carrier, the stuff that comes out is actually high frequency, right? Because that's what we want, because we want to send stuff in high frequency so that it's above all this noise in the atmosphere, right? Okay, so this is how we accomplish, this allows us to beat the noise, okay? And this is why we're doing all this trigonometry stuff, right? Okay, so if you did this, right, let's say you have I'm going to try to draw this. I probably should have just made a plot of it, right? Let's say you have I'm try to draw up here, right? This is the 120 hertz, 120 1 over s signal, right? And then you're multiplying this by a high frequency carrier signal. This is going to be this. I'm not even going to be, it's not even going to be close to 120 120,000 hertz, right? Whatever this is, right? Multiply these two functions together, what you get is something like this. Okay? You basically get like little envelope shapes, right? So this function, you see this part, right? This part corresponds to your original signal. Okay? That's your signal, right? And then this stuff in here, right? That's the carrier, right? Okay? Right? One thing you notice from this is that, okay, this creates kind of a double loop lob. So because, right, basically your signal and your carrier, they both can be positive or negative. So when you have two positive together, you get positive. But if you multiply a positive to a negative, it flips it to negative, right? So this is flipping up and down, 120,000 times per second, okay? Right? So the other thing you want to know, I just want you guys to notice, because we're going to not use this technique, right? Basically, the number of peaks, right, is twice as much, right? The number of peaks you get from the modulation is twice as much as the original, okay? Because you're flipping it up and down twice all the time, okay? Right? Okay? So in analog electronics, this is called a multiplier, okay? And so far, I have not taught you how we can multiply things together. You would think that would be pretty simple, right? I taught you guys how to add voltages, right? But I never taught you how to multiply things, okay? So multiplication is a little fun, and this is where the reason why this section in chapter 6 on feedback, functional feedback is important, okay? The technique is basically by using natural logs, okay? What is it? Using natural logs of diodes. Natural log, wait, it does make sense. Natural log nature of diodes. That's a very confusing phrase though, okay? What we're gonna do is we're gonna take natural log of, of your signal and your carrier, right? And when you take natural log of things, right, one of the properties of natural log is that when you have sum of two natural logs, it's equal to the product of that function inside that natural log. Okay? All right? So let's go back to our chapter 6 stuff, right? With this part that I didn't describe last lecture of functional feedback. Okay? So let's just go back to our operational amplifier, 411, right? And then we're going to put a input resistor in there. And then some other device, we're going to use a diode. But I just kind of want to have a general version of this, okay? Because if we apply golden rule number 2, what's golden rule number 2 again? V minus and V plus. So the non-inverting and the inverting inputs are the same, right? It's going to force it to be the same, okay? How do I know this, right? Since this side is tied to ground, this one is also tied to ground, right? It has to be, it's going to try to be at ground, okay? What that means is that whatever voltage is here is going to drive current over this resistor into ground, right? So the delta V across this is Vn, right? So Vn is going to equal to whatever the input current is, right? I think the book just calls it I, times that Rn, right? If you just set it up this way, okay? And you can solve this for I, right? So therefore I is actually Vn over Rn, okay? Nothing too difficult so far, okay? This current, right, if we do golden rule number 1, right, has to go through the feedback loop. It cannot go into the input, right? So therefore, whatever V out is, right, is going to be negative of some function, right, of I, right? And then we already know what I is. I is Vn over Rn, right? So whatever the output is, it's going to be some funky function, depending on what device you plug in there, right? That depends on Vn, and Rn is just going to be a constant because you're not going to switch out the resistor, right? Okay. Well, what is this function? Let's play with a diode, okay? We put a diode as our functional feedback loop instead, okay? I think I flashed this picture the last lecture, but we'll go through this much more slowly this time because we really haven't talked about this. Okay. In chapter 4, we described the diode. Remember, the diode is just a P and an N, right? Semiconductors sandwiched together, right? This creates this thing called a depletion zone, right? And the diode we're using is going to have a drop of 0.6 volts, right? It'll block current unless you go over that 0.6 volts, right? And that's what this picture is describing, right? So if we're doing the blue line, the 0.65 volts, right? You can apply voltage on both sides of this, across this diode, right? If it's negative, it'll block the current. You get no current, no current, no current, no current. But when you get close to 0.65 volts, then the current turns on, okay? In fact, the nice thing is that it turns on exponentially, okay? Okay. And if you go back to chapter 4, I think it's section 4.5, okay? You'll find this equation called the Shockley equation, okay? The same guy who invented the transistor, okay? The current as a function of this voltage can be modeled as some saturation current, I'll describe what that means in a second, okay? Times some exponential minus 1, okay? And it's the exponential part that we're really interested in, okay? This IS here is known as saturation current. This is the current that happens even if you reverse bias the diode. It's going to be a very small current, but you still get some, right? Because remember, the idea is that when you have a p-n junction together, you have this depletion zone that's blocking the current, but a little bit of current can still leak through, right? Because you have your semiconductor, it's still semi-conducting, right? It's just a very bad conductor, right? Okay. Okay. So the saturation current is going to be on the order of a picoamp, very small, right? Okay. And this VT, so E to the V, V is the voltage you're applying across here, right? And then over VT, VT is this thermal voltage, okay? And this thermal voltage is basically determined by the fact that you have, you're operating this diode at non-zero temperature, so it tends to T, right? Okay? And you just have, it's a combination of like Johnson noise and shot noise that's kind of, just moving things around, okay? Which is going to be on the order of like 25 millivolts. Very, it's, you can actually see it, but it's not a substantial voltage, okay? Okay, at least not compared to 0.5 volts, right? So it's like 20 times less than that, okay? So we're going to utilize the fact that you have this exponential behavior in the current, okay? What I'm going to do is I'm going to solve this, and well, I'm not going to do it. The book just says do it, and you guys can do it if you want. You want to invert this equation, okay? Right, you can solve this for this V here, right? The voltage across this diode is actually going to be equal to V sub t, right, times the natural log. It makes sense, right? When you invert an exponential, you get the natural log function instead, right? Right, 1 plus the current going across that diode, right, divided by the saturation current, okay? And remember that the saturation current is a picoamp, right? So any current going through that diode, you're going to get I sub diode over I sub s that's much bigger than 1, right? Okay? If this is much bigger than 1, you can just ignore the 1, right? Right? If it's 1,000, 1,000 plus 1 is just 1,001, right? Which is still approximately 1,000. Okay? Okay? So that's why you can get to this next step here. Okay? So now we can do natural log of things, right? So this is kind of nice, right? Because we have a natural log of a current, right? Because what we want up here, right? If we want to be going back to our goal here, right? We want to take natural log of voltages, okay? Let's see what happens. All right? So if you connect this diode to an op amp, right, following golden rule number 2, right, this forces, right, the current through the diode, let me draw this picture again, right? It's pretty simple. Vn, Rn, this is the diode, right? This is the current, right? This is the current through the diode, okay? The current through the diode has to come from Vn over Rn, right? I diode equals to In, right? O equals to Vn over Rn, right? This is what we just derived from just connecting this circuit to a op-amp, right? So we have this equation here. So we can replace I diode with that. And now you have V out, which is what's happening on out here. It's going to be equal to negative. Unfortunately, there's always going to be a negative because it's an inverting amplifier, right? Equal to the natural log of Vn over this complicated Rn over times Is, okay? It's just some number that, you know, whatever resistor you plug in, you multiply that by the saturation current, then you get a number on the bottom, okay? Right? So you have essentially V out that's proportional to natural log of Vn, right? And that's exactly what we want to do multiplication, right? Because what you can do is that, well, I'm going to make this VA, right? Out here, it'll be natural log of VA, right? If I make this input VB, out here, what will it be?
Natural log
VB, yeah, right? And now I have two outputs. If I tie them together, I basically have natural log of VA plus natural log of VB, right? Because when you just connect two wires together, you add the voltages, right? And that's exactly what's natural log of A times B, okay? Right? So now you have this thing stuck in the natural log, right? Okay? You can denatural logs it by just doing the exponential, right? You know, the anti-function of natural log is an exponential. And once again, you do a diode. Diode basically gives you these exponential functions, okay? Okay? So if you put in this natural log of AB here, right, and you just put it through a diode and a resistor, whatever the output is, it's going to be exponentiated. It's going to be proportional to the exponential of the natural log of AB, right? If you exponentiate natural log, you just get AB back, right? And this is how you can multiply together, okay? Right? So in order to multiply two signals together, VA and VB, right, you put it through each of its own op amp, right, with a diode across it. I'm going to run out of space here, right? You take those two output, join them together. Nope, not here. Join them together. You take those two output, join them together, and you put that once again through another diode. And then if you read the voltage out from ground, then you basically get VA times VB. Okay? Fun? No? So one thing to notice is that the diode is exponential in a very limited range. Okay? So you have to, so these devices will only operate with an input voltage of a very limited range. Okay? You can design them to be wider. Oops. Right. So what we're going to use this class is going to be this thing called an 8633. I'm not sure it's in your kit. If it's not, then we have a bunch of them in the box here. Okay. It has 8 pins. Okay. And it's a multiplier chip. Okay. And it does exactly what we just showed you. It takes two op amps, right? You multiply those two together, and then you add them together, right? And then you use another op amp with a diode in it to basically exponentiate that natural log function. Okay, right? You can find the data sheet here. Okay, it'll look exactly like your op amps, but it's because it's also 8 pins. Okay, it has 4 inputs. The left side is all inputs, so x1, x2 this is your input A, right? So this will be VA, right? And this will be your VB, and what's coming out is actually VA times VB here, okay? You can actually offset this if you want by adding a little Z voltage to it. There are some limitations before I let you go. So what happened is that this is known as the transfer function, okay? So whatever you put in on VA and VB is going to get divided by 10 volts, right? Remember, this diode has a very limited range of exponential behavior, right? That's why I always divide that by 2, so you have a small voltage, okay? Okay, all right? So whatever your output is going to be 10 times smaller, okay, than the product between the two. You can also add this, you know, if you want to have a constant shift up, okay? So I'll let you guys look at the rest of this data sheet. There's a few things that you probably recognize, like for example, slew rate, right? You can do 20 volts per microsecond, okay? So you guys are already familiar with slew rate, okay? The multiplication is good to about 1 to 3%, okay? So, you know, if you don't expect it to give you, you know, 10 digits of precision when you multiply things together. Let's see, what else is around here? Yeah, so it needs a supply voltage of plus or minus 15 volts, which is what we have on our breadboard, okay? There's also these characteristic plots. What kind of plot is this again? Bot plot, yeah. Whenever you start seeing decibel and frequency, there's always a bot plot. They didn't divide by like some resonant frequency because there's no resonant frequency in this case, right? But, right, when you look at this plot, what you should see is that, oh, you got a flat line, right? 0 decibel is good, right? That's when you have a gain of 1, right? You go over here, right? It starts dropping off to negative, right? So you have the negative 3 dB point, basically, you know, maybe around 800 kilohertz. So you probably don't want to do any multiplication beyond 500 kilohertz, okay? Which we're not going to do anyway. Okay? So there is some limits on how fast it can process things. And I think that's why in the lab, I think I have you guys have the carrier wave around 50 kilohertz, right? So this cannot do like AM and FM transmission for you, but it's just a good demonstration, okay? Any questions about how things get multiplied together, how this chip works, and why we're doing it? Okay, next time I'm going to teach you